Delaware Tech, Chemistry 110, Chemical Quantities and Reactions Continued, Limiting Reactants. Limiting reactants tell us which reactant runs out first. That's the reactant that limits how much product we can make. So, let's think about something not chemistry first to think about limiting reactants or limiting reagents. Let's say you need 2 slices of bread, 1 tablespoon of mustard, and 3 slices of salami to make a single salami sandwich. That's what you need. 2 slices of bread, a little bit of mustard, 3 slices of salami. And someone gives you 200 slices of bread, a gallon of mustard, which is about 256 tablespoons of mustard, and 3 slices of salami. How many sandwiches can you make? Well, let's look at how many sandwiches you can make from each ingredient first. You have 200 slices of bread. That's enough to make 100 sandwiches because you need 2 slices per sandwich. We have 200 slices. That's 100 sandwiches. We have enough mustard to make 256 sandwiches. But we only have enough salami, 3 slices, to make 1 sandwich. So which one runs out first? Well, obviously, it's the salami. That limits how many sandwiches we make. We got tons of bread. We can make a lot of sandwiches. We got tons of mustard. We can make a lot of sandwiches. But we only have 3 slices of salami. It limits how many salami sandwiches we can make. It limits it to 1 in this case. So, how many can we make here? We can only make 1. And that we can think of as the product in our chemical reaction. So, in any chemical reaction, if you have 2 reactants and somebody says, I have this many grams of this and this many grams of this, how much product will I form? Well, first thing you have to figure out is which one's going to run out first. And that means you need to do 2 separate calculations if you have 2 reactants. If you had 3 reactants, you need to do 3 separate calculations. So you already learned how to do stoichiometry calculations, but now you're going to do them in pairs. 1 for one reactant and 1 for the other reactant. And you're going to calculate how much product from each reactant, assuming that you have lots of the other reactant, that it's in large excess. In other words, first you're going to look at reactant A and assume you have all the B in the world, it's not going to run out, and say, how much product can I make from reactant A? And then you're going to look at reactant B and say, how much product can I make if I've got tons of A to work with? How much will I make? Well, whichever one makes less product, that's the one that's going to run out first. That's your limiting reactant. It is the only one that's important. In fact, you can, once you've figured out which one's the limiting reactant, you can cross out all the math you did for the other reactant, which we call the excess reactant. So the limiting reactant is the reactant that runs out first. It determines how much product you can make, and the excess reactant is the one you have, is the other reactant, the one that didn't run out during the reaction. So let's look at this in practice. We have, if you have 10.1 grams of magnesium, that's magnesium metal, and 25.6 grams of hydrochloric acid, HCl acid, are reacted, how many grams of magnesium product are produced? Now, you might be tempted to say, oh, well, I've got 2.5 times more acid than I have of magnesium. The magnesium will run out first. No, you can't go by the grams. Remember, each substance has its own molar mass and therefore has its own mass per number of moles. And in a reaction, sometimes reactions use a lot of moles of one thing and only a few moles of another. So that confuses things as well. So you have to determine which one is going to run out by calculating the whole thing. You determine how much product you can get from 10.1 grams of magnesium with a lot of hydrochloric acid, and then you do a second calculation and say, I have 25.6 grams of hydrochloric acid and I have all the magnesium in the world, I'm not going to worry about magnesium. And then you ask yourself, which one made more product? Well, the first thing you have to do is figure out the formula for each of your reactants. Magnesium and HCl acid. Well, I've given you HCl, hydrochloric acid is HCl, and magnesium is just Mg. So that's easy. The second thing you have to do is determine the reaction type to figure out what your products are going to be. Well, you already know that magnesium with acids is a single replacement reaction. It's a element plus a compound will make a compound plus an element. And it's a single replacement, which means the magnesium will replace the hydrogen. Usually, if you have a metal in a reaction, either a metal will replace a metal, or a metal will replace a hydrogen, or a hydrogen will replace a metal. So hydrogen will behave like metals in single replacement reactions. So now you'll have the magnesium with the chloride, but you have to figure out the formula for that. Once you know it's a single replacement, you know that magnesium will be with the chlorine and hydrogen will be by itself. So you need to complete the reaction. Well, you'll need to use crisscross simplify to get the formula for magnesium chloride, and H will be left by itself, but we know that H is not the elemental form of hydrogen. Hydrogen is a diatomic element. So H will be H2. That's how it's formed, that's how it's seen in nature. Its elemental form is H2, a diatomic molecule. And then magnesium chloride is MgCl2 because magnesium is +2. The chloride is -1. We crisscross and we get 1 magnesium, 2 chlorines. You'll notice that this reaction is actually also a redox reaction because we're going from magnesium metal, which has no charge, to magnesium chloride, which has the magnesium has a +2. And the hydrogen is going from +1 in HCl to 0 in H2. So magnesium is being oxidized, the hydrogen is being reduced. So it's also a redox reaction. All single replacements are redox reactions, but we're going to call this single replacement. That's the main type of reaction here. We now have the reaction. The next step is to balance the equation. We need balanced coefficient values in order to do our stoichiometry calculations. So we balance it, and we see that we have 1 magnesium plus 2 HCl's will produce 1 magnesium chloride and 1 hydrogen gas. So it's a 1 to 2 to 1 to 1 ratio. And those are our fixed ratios. We know, if we know how many moles of any one of these, we know how many moles of the other by the ratio. And now we need the molar masses. Well, we're given masses of magnesium, we're given masses of HCl, and we're asked for the mass of the magnesium product, which is magnesium chloride. So we need all 3 molar masses. So I'll pause here. Let's see if you came up with the right answers. Magnesium is right off the periodic table. Hydrogen gas, we don't need it, but I included it anyway. HCl, you're just adding an H plus a chlorine. You get 36.461. And magnesium chloride, you have 1 magnesium and 2 chlorines, 95.211 grams per mole. These are all in grams per mole. So now we have our molar masses, we have our balanced equation coefficients, we have everything we need to write out 2 separate, independent stoichiometry calculations. One using 10.1 grams of magnesium, and one using 25.6 grams of HCl. They are not in the same equation. You are then going to figure out how many grams of magnesium chloride each one could produce if you had a lot of the other reactant. So we create 2 maps and 2 problems. So for magnesium, we're going to change our magnesium grams to magnesium moles. That's the first conversion factor shown here. Then we turn moles of magnesium to moles of magnesium chloride. Well, that's easy. It's a 1-to-1 ratio. And then we turn moles of magnesium chloride, 2 grams of magnesium chloride using its molar mass. And we find that 10.1 grams of magnesium with enormous amounts of HCl available produces 39.6 grams of magnesium chloride. That's only if we had an enormous amount of HCl. So now we just look at HCl separately. And we see that if we start with 25.6 grams of HCl, we convert the grams of HCl to moles of HCl to moles of magnesium chloride, and then moles of magnesium chloride to grams of magnesium chloride. And you'll notice the last conversion factor for both of these is the same. because you're converting moles of magnesium chloride to grams of magnesium chloride, you can use the same conversion factor. And in this case, we only get 33.4 grams of magnesium chloride if we reacted this much HCl with a lot of magnesium. So the question is, which one produces less product? Well, clearly the one that produces less product is the HCl. The HCl will run out first. You'll only make 33.4 grams of magnesium chloride. You will never be able to make that remaining 5.2 grams because the HCl will run out. It doesn't matter how much magnesium you have. The HCl runs out first. It is our limiting reactant, and therefore it is the only calculation we care about. The other calculation is now just a fantasy. It would be what you'd get if you had lots of HCl, but it is not what we get. So you find that 33.4 grams of magnesium is the answer here. It is the amount you get from the amount of HCl because HCl is our limiting reactant. It's the one that runs out first. And you can't just look at the original question and guess the answer. You have to do the calculation, and you have to be careful to determine which one will produce the right calculation for your product. So, here, that was your first example. Here's a practice problem. 10.3 grams of aluminum metal are reacted with 51.7 grams of aqueous copper 2 sulfate. All right, we did something like this before with copper 2 sulfate. It was with iron before. Now we're reacting aluminum, and we're asking how much copper metal will be produced in moles, and then how much will be produced in grams. So we can stop at the moles and compare moles for each of these two reactants. We can look at the aluminum metal and say, how many moles of copper will we make? And then we can look at the copper sulfate, and we can say, how many moles of copper will be produced from that? And whichever one is less, that's the important one, and you can convert the lesser of the two to grams, and that'll be your correct gram value. So you're going to do what you always do, determine the formula of each reactant, aluminum plus copper 2 sulfate, type of reaction, this is another single replacement. You're going to complete the reaction. Remember, aluminum makes +3 ions, so +3 with sulfate is -2. You need to crisscross simplify to get the formula, Al2, parentheses SO4, close parentheses 3. In other words, you need 2 aluminums for every 3 sulfates in this formula unit. And now we have our equation, but we still need to balance it. I'm not going to go over how to balance it. You should know that by now. You can review the balancing section in a previous unit if you're still having trouble with it. So we have a ratio of 2 to 3 to 3 to 1 of our reactants and products. And all we need now are our molar masses. We're given grams of aluminum. We're given grams of copper 2 sulfate. We're asked for grams of copper. So we need those 3 in grams per mole. And I just threw in one more in there, the aluminum sulfate at the end, just for fun. You don't need it in this particular problem, but you might need it in a follow-up problem. So now we have all our conversion factors. Now we create 2 stoichiometry problems, one for aluminum, one for copper 2 sulfate. We start with aluminum. We turn aluminum grams to aluminum moles. We turn moles of aluminum to moles of copper, and we get 0.5726 or 0.573 moles of copper. If we start with copper sulfate, we get only 0.324 moles of copper. So clearly, 0.324 moles of copper is less than 0.573 moles of copper. That means we're really producing the lesser of those two, because that means that our copper sulfate, the second reactant, is going to run out first. Even though we've got 5 times as many grams, it's going to run out first. So you have to do the calculation to determine that. You can't just look at the problem and guess the answer. So we see that the only reactant that we're concerned with the math on is the copper sulfate problem. And that tells us exactly how many moles. And we can give our rounded answer of 0.324 moles of copper, but use your unrounded value to convert it to grams of copper using the molar mass of copper, 63.46 grams of copper per 1 mole of copper, and that will give you the number of grams. Now, you could have done this by doing it all the way out to grams twice and say which one's the lesser grams, but that's a lot of extra work. You don't need to do that. Since you're asked for moles first, compare the two moles values. That's okay. Whichever one's the lesser moles, remember, it's still copper. Moles of copper versus moles of copper. You can compare those, and you can tell which one is the limiting reactant. In this case, the limiting reactant is copper sulfate, and the excess reactant is aluminum metal. So let's take a look at this last example. So here we have, it says if 3.56 grams of phosphorus, P4, this is actually white phosphorus. Phosphorus has 4 different what we call allotropes, forms of the element. White phosphorus, also known as yellow phosphorus, is P4, are reacted with 0.433 grams of hydrogen or hydrogen gas. How many grams of product will be produced? Now, I'm going to have to tell you what the product is because this is not something you could guess with the knowledge that you have from these courses. But let's look at this problem anyway. So first you have to determine the formula of each reactant. Well, I've given you the formula of the phosphorus, P4, and hydrogen gas you already know is H2. So that's pretty straightforward. Second, you have to determine the reaction type. Well, you have an elemental form of phosphorus and you have the only elemental form of hydrogen. So since you have 2 very simple compounds, you might guess that these are going to combine in some way in a combination reaction. So we don't need to do anything special since the instructor would just tell you what the product is, since you wouldn't be able to guess what it was otherwise. In this case, you're going to write the products. I will tell you the product. It's PH3. This is phosphorus trihydride, also known as phosphine to chemists, but you call it phosphorus trihydride. You don't need to use the crisscross rule because there's no metal in here. It's not an ionic compound, so you won't need it in this particular case, but you might in other situations. Now you're going to balance the equation, and you should be able to balance this equation using the rules we've already discussed, and you would get 1 P4, or 1 white phosphorus, plus 6 hydrogen, or hydrogen gases, produces 4 PH3s, or phosphorus trihydrides, 1 to 6 to 4. And we're going to need some molar masses because the problem says certain number of grams of phosphorus reacted with a certain number of grams of hydrogen, and they want to know how many grams of product. So we need molar masses for all 3 of those. So I'll pause here for a second, let you calculate those. Okay, I'll now show you the values for those. And they're written right here in grams per mole, as always, as molar masses should be. And now we're going to create our 2 stoichiometry problems. So you can make a map that shows you're going from grams to moles to moles to moles. Grams of moles to one thing, moles of the one thing, the moles of the second thing, and then moles of the second thing to grams of the second thing. Or you could just write the maps directly as formulas. So we have 3.56 grams of P4. We're going to calculate how much product is formed from that, assuming there's an enormous amount of hydrogen gas available, so it doesn't run out. And then you're going to calculate how many grams of product you'll make from 0.433 grams of hydrogen gas, assuming you have a lot of phosphorus available, so it doesn't run out. So you do the 2 calculations. 1 for 3.56 grams of phosphorus, and you get 3.91 grams of PH3. And if you use instead the 0.433 grams of hydrogen gas, you see you get 4.87 grams of phosphorus trihydride. So this tells you that the first reaction is the one that's going to actually happen. The first calculation is the correct one. You can just cross out the second calculation. It is totally meaningless because you know the phosphorus will run out first, and therefore the phosphorus is the limiting reactant, and that means the amount of product we will actually get is 3.91 grams of PH3. And we'll stop here.